Welcome everyone to today's webinar. We'll be going through CreativeLi and some of our work as IAB Europe to streamline creative assets, lightweight them, and ultimately reduce emissions. Just some housekeeping first. We'll be covering four things. First, why compression matters to the digital ad ecosystem. Second of all, some technicals on image compression, as well as how CreativeLi works. Then we're going to talk a little bit about video and some ad tag testing we've been doing. And then finally, share some best practices that have been surfaced throughout this process. As you can see, we were originally planning to do this through Zoom. We don't have a Q&A function right now on Meets, I believe, so the chat will work fine for any questions. We'll group them up and take them at the end of each section or at the end of presentation. So first of all, let's talk about the value proposition of better compression. Why does it make sense to care about the efficiency with which we compress different assets? Well, first of all, we're obviously approaching this from a carbon footprint perspective. If we look at the global media sustainability framework, we're really focused right now on delivery, where a lower payload is a decarbonization lever. What that means is by lowering the payload of the assets you send through, that means you directly lower your emissions. There's actually a linear relationship between the emissions in this stage and the payload itself. But apart from that, compression also matters across other considerations. First of all, being cost. So reduced file size means less resource usage when storing and sending data. Latency. So by reducing the file size, we also reduce the time it takes to load everything on a page, including the ad itself. That also means there's an impact on the user experience. And there is a bit of work here that shows that a better user experience with lower latency leads to better results across the internet. Now, there's been a lot of research in this particular area. We can identify some hypotheses for the impact of better compression for different stakeholder groups. First of all, in terms of a campaign, the lever of action here would be to request that your partners implement efficient compression. From a campaign perspective, you don't necessarily have that much agency over the compression of the assets that are delivered to the user. And the potential outcomes here would be to reduce the footprint of the campaign and potentially improve performance. We're doing some case studies in particular on that point. Now, from an ad server perspective, what you can do is implement best practices in asset transcoding and minimize data waste. So with a lot of these recommendations and a lot of this work, we're mainly focused on ad servers since they have control over the compression process of different assets, and they are the ones that can effectively implement all of the different guidance points. The outcome there would be to reduce the storage carbon footprint and then also reduce the cost of storage. And then finally, from a publisher perspective, here there are some things you can do directly when setting up your site for ads. So for example, we've been looking at things like lazy auctions that only load when the placement is in a certain distance from the viewport. But mostly, again, this will go back to the ad server. So it also depends on what kind of controls the publisher has over the ad server as opposed to the ad server. Now, obviously, there's a point here about reducing the carbon footprint of the website, but there's also a point of value here with respect to latency in UX, as there's a lot of research that suggests that if everything on the website loads faster, as a virtue of the compression being better, then the users stay on for longer. Now, looking at some of the prior work on latency, we can look at a few different examples and case studies where we have meaningful insights. First of all, A/B tests on Amazon. This is one of the most cited studies back from 2006. They observed that 100 milliseconds, 0.1 seconds of latency results in a 1% drop in sales. Google did something similar for search results. A half a second was a 20% drop in traffic. Walmart did the same kind of A/B test where they tried to reduce latency and noticed that there was a 2% increase in conversions for every 1 second improvement in latency. Then there was an analysis of a lot of e-commerce websites that showed that the best performing ones had a load time of 1 second. And actually after 4 seconds of loading, then the performance starts to drop rapidly. And then finally, from a publisher perspective, the BBC did similar testing, found that they lose about 10% of the users for every additional second of loading time. So compression, really, we care about it from a carbon footprint perspective, but there's actually a very tangible other side of the coin here. With respect to other KPIs. Now, let's look at some more newer case studies as well. According to Google, they did an analysis of a lot of websites. That's how they also set up their own kind of standards around loading with Core Web Vitals. They found that the best performing sites have these kind of characteristics. And these are different metrics that essentially look at different components of loading. So for example, LCP is the largest contentful paint. It's about the largest asset on the image and how long it takes to load. Now, if we look at the Financial Times, they saw that with 1% more load time, they lose about 4.6% of their users, 3 seconds, 9%. If we look at a couple of brands, on Vodafone's website, there was a 31% improvement in LCP that boosted total sales by around 8%. And then finally, if we look at Renault, if they did 1 second LCP improvements, achieving different final LCPs, and they saw that the results were actually pretty decent with respect to conversions. And the bounce rate effect I would highlight, because bounce rate is really one of those levers where latency ends up destroying value, because additional latency means higher bounce rate. So viewers visit fewer pages, essentially view fewer ads, and therefore revenue goes down for publishers. Okay, now how does IAB Europe come into the picture here? We've launched the Sustainable Creatives Task Force earlier this year with a collaboration of Net Zero and a couple of their global brand supporters. So this task force has done a few things. First of all, distributed an RFI that was to understand how exactly ad servers deal with assets, and in general, any kind of ad tech platform that handles and hosts the asset itself. We examined prior research, white papers, industry standards, such as the Lean framework, to understand, what the industry is going by at the moment. And then finally, perform some testing on image and video files, as well as tags, to understand how they can be optimized. And the methods developed during the testing are what eventually made it into CreativeLi that we launched quite recently as well. Now, we're not done yet, but we are in a position where we can give a pretty robust update on what we've done so far. We also want to develop some case studies, effectively A/B tests with optimized and unoptimized assets to understand the impact on campaign performance. There is a gap of work here. I haven't really found anything directly on the impact on campaigns. Second of all, we want to expand CreativeLi's capabilities in line with our testing on video and tags. So as we discover more and more things in testing, we want to make all of those capabilities available to the industry as well, so you can also understand what's happening with your assets and how you can best optimize it from an ad server perspective, perhaps. And then finally, we want to explore how exactly we can take all of these best practices and work with the industry to implement them and to ensure that everyone's essentially participating in this common strategy of efficient compression. That's pretty much it in terms of the setup for this webinar. Now let's dive into compression technicals. Now this will get quite technical, but I promise that all the information here is actually useful in terms of understanding how compression feeds into this entire process on the ad server side. So we're going to look at a JPEG example first. The first thing usually is done to images to begin the compression process. We convert them to a different color space. So images normally show up in RGB on your monitor. We convert it to YCBCR. There's a luminance channel and then a blue and a red chroma channel. And what we do here is we downsample the chroma channels. So that means we take an average, let's say a 4x4 pixel area, and we take the color that is the average of the colors in that pixel area. Why do we do that? Because human perception is less sensitive to averaging out color than it is to the brightness, which is this channel right here, the Y channel. Now, here, I know this looks complicated, but it's really not that complicated. We take an 8x8 area of the image, so 8x8 pixels, that we call that a macro block. And there's really cool math that shows that every macro block can be represented as a weighted average of each of these little boxes here. What those are essentially cosine waves of different frequencies, one going to the right, one going down. And as you combine those, you get a grid, and you can express any kind of 8x8 pixel macro block using weights and those cosine functions. So we turn the image effectively into a big array of all of these coefficients, and that is when the compression begins. We apply a quantization table. What this effectively means is that we divide everything in this original table by this table, and that's how we get the quantized coefficients. And by the way, this is where we have loss in lossy compression, because after we divide, we round to the nearest integer. Okay, that is how we shave some of the information out the image, and that information can never be regained. So this is now that 8x8 pixel block, and we have a lot of these 8x8 pixel blocks that end up making the image itself. And because it has a lot of zeros, now that we have applied quantization, it's really easy to now do something called entropy coding to reduce the file size and effectively store all of this information more efficiently. So then when we take all of that, we put it into the JFIF container. That is the .jpeg that you see in your computer. We have a JPEG file that is ready. All you need to do now to get the original image is simply apply all of these transforms in the reverse order. Now, even if you understood none of that, what's important to understand is that the quantization table is what affects the quality setting in most cases, right? So if we divide by larger numbers, what that means is that we're going to be shaving off a lot more of the information. If we divide by smaller numbers, we shave off less of the information. That gives us the trade-off between file size and quality in the final file. So if we select a quality of 60 when encoding JPEG, for example, the standard quantization table will be scaled by 4 or 5 times. That means we'll shave off more information when we end up reducing the file. And we also have some color downsampling, which is what you see here. Again, the process of taking a few pixels and averaging out the color between them. So we essentially lose some of the color in that process, but again, gain some file size reduction. Now, the entire system of JPEG compression works on these 4 facts. A, that again, you can represent any 8x8 block with cosine functions. B, that most blocks are actually adequately represented using mostly the lower frequency cosine functions. So if we go back here, these cosine functions matter much more than these. That means that when we quantize, this is actually a pretty good representation of the image. And then human vision is less sensitive to color than it is to brightness. That is why we can get away with things like color downsampling. And then finally, it also leverages entropy coding to reduce the file size after we have come up with all of these zeros. So what's important to understand here with respect to image formats then? The image format itself will give you a standard encoder called the reference encoder. That's called a libjpeg in the case of JPEG. And then it also gives you a container. So the format isn't technically just JPEG. It's the JPEG codec and then the JFIF container. But the format spec does not give you a standard scaling of the quantization table. And it does not actually constrain codecs to using the reference quantization table either. What that means is that there is no standard quality scale across image format encoders. And we have different encoders that can use wildly different approaches, some of which we'll explore now. So looking at different formats for a second, the reason why some formats end up producing lower file size files is because they simply apply more transformations to the original data. That means that they also consume more resources during the encoding and decoding process. And there's a kind of trade-off between CPU load and compression ratio. So we see that WebP, for example, has a bigger macro block. So it takes 16 by 16 areas of the image, for example, also more complicated entropy coding. And then AVIF, even more complicated transform with a sine transform, and then even more complicated entropy coding. That's why it delivers better results a lot of the time than the other two, but also consumes more CPU. And this is important because for AVIF, for example, if you look at hardware acceleration, it's not really a thing yet for a lot of devices. So that is how exactly quality setting works and what exactly we're affecting when we're changing the quality setting. Now let's talk about the other side of the equation, that is quality. Now, how do we measure how much quality was lost after compression? How do we measure the difference between the original image and the compressed image? One way is to use something called SSIM, Structural Similarity Index Measure. It essentially takes, again, small areas of the image and compares 3 things: the luminance, the contrast, and the structure. So in this particular case, there's a set SSIM difference between the original images and the images below, I think. And SSIM is a pretty decent measure. Studies have shown it also correlates better with how humans perceive images as opposed to things like peak signal to noise ratio. But there's another option here as well that's quite interesting. That's better ugly. It's been developed by Google based on their model of how human perception works, like which differences matter more to the human eye. It incorporates things like the fact that we don't see green as well as other colors. And it gives you a very cool heat map of the perceived difference between two images. So it tells you that humans looking at these two images will start to see differences first in this area, and in this area, and in this area, and in this area. And if we'll take a closer look, you can start to see that actually there is a perceivable difference where the heat map indicates that. And it's actually because of the JPEG format itself. It sometimes struggles to handle text, especially smaller text. That is because the text requires higher frequencies if you look at the DCT table. So there's one of these assumptions that we can represent all of these images using the lower frequencies actually doesn't hold true in the case of text in images, and that is why a lot of the times people suggest you don't use JPEG if you have fine text, because you'll end up introducing a lot of artifacting around it. But it's usually okay with the larger text because it doesn't actually show up in the within the macro blocks themselves. Okay, now that we've covered all of that, let's talk about how CreativeLi works, because we have all of the components in terms of the required information to understand it. All CreativeLi does is it takes your master file, which has to be a high quality, relatively uncompressed, lossless file, like a PNG. It takes a target for either of these two metrics. It used to be based solely on SSIM, but now we've developed a better ugly version as well. And then it sends quality settings to the encoder, which then develops a profile. That's the compressed file in one of the three lossy formats. That's compared with the original master, and then the metric is given back to CreativeLi. We test whether it meets the target or not, and if not, we continue the loop until we find the optimal quality setting. And we do this across three formats, that's JPEG, WebP, and AVIF, all in the lossy mode. Why is this better than what the industry currently does in a lot of cases? So let's take this PNG again, the master file, and let's look at three different ways to approach compression. First of all, we can look at previous standards. So if we look at the lean, for example, it gives you a max of 200 kilobytes. That's obviously quite large. It's actually pretty close to the original master file's weight, which makes sense because lean came out a few years ago and things have been getting more efficient since then. We can go with a standard, just JPEG encoding using some kind of heuristic for the quality setting. So what you'll find pretty common in recommendations is a quality setting of 75 for web, which tends to be okay in most cases. But in this case, it would actually produce an image that is probably a bit overcompressed, as you can see from the SSIM being 0.912. And actually, I opened up the file. It does look a bit overcompressed. Or you can use CreativeLi with an SSIM of 0.95. That's our default, by the way, which will give you a JPEG that weighs a bit more than the standard encoding using a heuristic. But you've ensured that the quality is actually pretty decent. So in this scenario, following a standard quality assumption of setting it to 75 for web, the file would be overcompressed. And the opposite scenario could hold true as well, where essentially the standard quality setting is not enough, and there's more compression that would be possible without compromising on fidelity. So if we look at why it's better than current approaches, it's essentially 5 reasons. The first 2 are the ones I just described. It extracts as much compression ratio as possible while also protecting against artifacts and quality loss. That's essentially the Goldilocks zone of compression. It can optimize for a visual metric or for a given file size. So you can go through the visual metric, but you can also use the benchmark mode to just meet a certain file size limit. This actually lends itself quite nicely to different kinds of transcoding logic that can be based on one or the other. And then CreativeLi also optimizes assets across formats. So you always know which format is the most efficient for that particular image. And you also know exactly how quality scales with size through the graphs that we provide. And then finally, all of this challenge is essentially simplified to one input, and that is what should be the target for the psychovisual metric, which then gives us a lot of leeway in terms of work for further development to optimize this process. This is better than having quality setting, for example, because as I explained before, quality setting is not standard across different codecs, whereas if you have one target for the psychovisual metric, it's actually easier to do a lot of cool stats and optimize everything. Why is it not perfect? A couple of reasons, and essentially compression is always going to be a bottomless pit. It's actually impossible to come up with something that solves the problem of optimized compression once and for all. First of all, as a metric of distance of the compressed image from the master, that means it's a relative metric. It's kind of hard to set a standard target for any kind of visual metric. So there's no kind of objective, absolute idea of what is good enough visual quality. And because these metrics are always relative, they will depend on how much fidelity, how much information is in that original master. Okay, so if you put a lot of stuff in that original master, say for example, you're using assets, raw assets that are of a really high file size for no reason, then you will start to see SSIM drop even with the higher quality settings across formats. So there needs to be a kind of initial reference point as well that is kind of common in order to be able to make use of visual metrics in a kind of standard way. Or you need to be able to come up with a way to set the target based on some of the image's characteristics. CreativeLi also takes a few seconds, which isn't something that's unheard of in the world of transcoding. It's usually around under 5 seconds if it's hosted locally on the web server. It's about 10 seconds if it's a really large image. And we are currently performing tests to understand what exactly we can extract this information from these images in order to optimize the search algorithm and essentially have it make better guesses. There's also the 3D graph you see on the right, where one of the features of an image that we're exploring is the original image's resolution or area. And we've actually plotted these rate decay curves that give us the limit of compression for each format, essentially telling us which format is better for each image, et cetera, et cetera. There is always going to be one format that tends to outperform the rest across different quality settings, but we also need to take account of things like the CPU usage, for example. All right, we're about halfway through. Any questions so far? All right, seeing as there are none, we'll dive into video. Oh. We'll actually get to the point of where this kind of logic needs to be applied, because I wouldn't even say that the tool itself needs to be applied, right? It's more about the logic that the tool encapsulates. But I'll get to the point of what exactly happens when you upload an image to a platform and how exactly it should be compressed. Okay, so it's a good question, Juan. We'll just get to it in a few minutes. So let's talk a little bit about video. Video codecs generally work quite differently from image codecs. So for example, they do things like track the changes in between frames rather than store the information of the frame by itself. But certain concepts are quite similar. So if we understand how CreativeLi works, which judging by the number of questions, I'm going to assume we all do, we can just replace a few things with some other concepts related to video. So first of all, instead of looking at image formats, we're looking at video codecs. So all of the produced files are MP4s. That's the common container that all of these codecs can be configured to use. However, there are different compressors, essentially. We replaced the visual metric SSIM with VMAF, that's Video Multi-Fusion Assessment Method, which was developed specifically for video by Netflix. Netflix, of course, has a big task in its hand with respect to optimizing streaming. And then we replaced the quality setting that usually controls the quantization tables. So it controls how much the information is compressed with CRF. And that is a variable that describes the quality loss between frames of the original and the compressed videos. Now, to understand CRF, we have to talk a little bit about constant bitrate and variable bitrate encoding. So most codecs will let you do both. Some codecs will only let you do one of the two. Most modern codecs are moving towards variable bitrate encoding, but there still are use cases for CBR as well. Now, the way CBR works is that you have a fixed bitrate throughout the entire duration of the video, which you select when you go to encode. And this ensures a constant data rate and a pretty predictable file size. However, there are some issues that occur, which we can understand once we look at how VBR works, which essentially adjusts the bitrate dynamically. You can have a target bitrate or a max bitrate, but it's allowed to float. And it floats in accordance to maintaining a constant compression factor called the CRF, which essentially looks at the difference between the original frame and the compressed frame. So when you have a constant bitrate, obviously it will suffice in a lot of cases for what you want to do, but there might be some scenes with a lot of action, for example, where more bitrate is required to maintain quality. Why? Because more action means more changes between the frames, which means more information, and at some point that information might be more than what the bitrate can provide for. That's called bitrate starvation. It's also the reason why you see all of these funny artifacts, sometimes watching videos or sometimes on TV if something has gone wrong on the technical side. There's also the other case where under CBR we would have an excessive bitrate, where it's like a static scene and less bitrate is required to maintain quality. So if it's like a black screen in between shots, for example, you don't really need all of the bitrate that you have if you're using CBR. If you're using VBR, it automatically lowers the bitrate because you can maintain a CRF level without necessarily using up all that bitrate. So when we're talking about applying creatively on video, what we're really talking about is finding the right CRF that effectively acts as a quality setting for each individual frame. It actually ends up affecting the quantization tables themselves. We've done the exact same thing we've done with image formats with video. One of the reasons why we haven't made it available is because it consumes a lot more resources, and so therefore it would be kind of difficult to do that over web. But we do have data that is kind of similar in structure to the data we have for image formats. So looking at the different options for codecs, we've got X264, that's the kind of traditional codec, similar to JPEG. I guess if we were to draw an analogy with images, we've got X265, that's a newer version. We've got VP9, that's been developed by Google. And then we've got AV1. So VP9 and AV1 are effectively WebP and AVIF. And in most cases, as we saw with image formats, the AV1 based ones outperform the VP9 based ones, but there are some cases where the VP9 based ones outperform the AV1 based ones as well. So in this graph, towards the top on the left means better. It means for a lower size, we're getting a better quality metric, a better VMAF. Now, what really matters here as well is the speed it takes to do all of this. Because with video, when you're dealing with a lot of frames, effectively a lot of images, the speed can actually end up being quite impactful. It's also one of the reasons why we haven't made this available through Creatively. And there's good research that shows the trade-off between speed and quality for different encoders. Now, for art testing, what we did is we tried to standardize the kind of time variable. So we looked to set everything with CPU settings that deliver similar encoding speeds as well. But it just complicates the problem just a tad bit further at the point at which you also have to figure out how much CPU time you can allocate. Now, we'll go back to why exactly this matters in the kind of next section of recommendations. Now, when it comes to video, apart from what we're doing on like a video asset level, we're also looking at tags and trying to understand data transfer at the ad tag level. Specifically, we're testing out cases such as the ad tag moving in and out of the viewport. We're loading the ad tag in different environments, different device types, different bandwidth limits to understand A, what kind of data wastage exists, and also B, how exactly the ad tag adapts to different environments. So, for example, in this particular case, we see that all of the loading happens below the fold anyway. So this particular tag is not very efficient. We're also going to be looking at things like how much buffer we actually need and whether there's any waste on that side. In general, all kinds of metrics tied to data to understand where we can identify waste and where the data can be reduced. All right, and with that, we'll move on to the final section with some of the best practices. So what have we learned from all of this work and what would we ultimately recommend when dealing with different assets? So first of all, Juan, we'll get to your point. I think it's the most important one. There's a lot of double compression going on, actually a lot of multiple rounds of compression going on at the moment, and this is in no likelihood quite inefficient. It essentially means that we're losing both in terms of quality and file size, so the compression doesn't end up achieving its original objectives. Now, there are a few reasons why multiple rounds of compression end up harming your creatives. First of all, for lossy formats, once you lose information, you can never regain it. Okay, so if at any point in a chain of transcodes you go to a certain quality setting, say 65, you can never go back to any higher quality setting. You've lost the information in that file forever as part of the quantization process. So there are cases where you might see transcodes moving the quality setting up again. You are just losing out on file size. You're not gaining anything with respect to quality. This ends up being quite inefficient. Second of all, for lossy encoders that again apply chroma sampling, you are chroma downsampling multiple times. That means that the colors are being averaged out in a region of, say, 8 by 8 blocks or something, or 4 by 4 pixels multiple times. And each time you do this, more and more noise is being introduced into the average as well from the quantization process. This degrades the perceived quality, and you start to get this effect where the tonal changes, like between colors, becomes less smooth. You have these hard outlines around objects, etc., etc. And this is actually exacerbated if you move between formats. So if you're moving between formats and the color sampling doesn't work in the same way, you're applying all kinds of averages to the color channels. You end up having images that look a lot worse than they did originally without a file size saving. So here, for example, we can see we've done a couple of JPEG encodings. Note how the histogram changes a little bit because there is a lot of noise coming into the average. By the way, even if there is no perceivable negative impact on the image quality, it can ultimately be inconsequential to compress before the ad server stage, exactly because once you upload to the ad server, different transcode logic will apply. Okay, so if an ad is transcoded from JPEG to WebP, because your agency said, wow, okay, we're going to sell you some green campaigns, we're going to make all of your creatives WebP, it's going to be great. Yeah, no, nothing's going to happen, because once you upload it to the ad server, most likely will be transcoded to a kind of different format, okay? And that renders the initial transcode ineffective. This actually applies more to video. It's more important there because the compression is more impactful as well. In some cases, some static image files might be preserved, but I've done a lot of testing, downloading ads that are served through different tags, and I see the same quality settings everywhere. It's not really a dynamic system at all for images. So for example, in this example, you have the PNG, I think. You make it into a WebP, everything looks pretty smooth. exactly because WebP uses 16 by 16 macro blocks, exactly because it uses a different kind of approach. But then you turn it back into JPEG on the ad server level, and then you start to see even more quality loss in the original. This is also done, by the way, not because your ad server is evil, but for compatibility purposes, because it makes the entire process simpler if you apply just one transcode to all the images, etc., etc. But actually, it's a bit more complicated than that. We'll get to that in a second. Second of all, use modern lossy file formats. Now, they're not always available as options, but in a lot of cases that they are, right? So when you can, do use WebP and have WebP in the lossy mode, because you can actually get very decent results, even if you don't use any kind of dynamic process, just by using some smart heuristics. In this particular case, I got this result from CreativeLi from an original 300 kilobyte PNG. We can get down to a 19 kilobyte AVIF. Okay, AVIF maybe not the most commonly used format, but the WebP 20 kilobytes also great. Compare that to the lean max of 200 kilobytes. That's 10% of the benchmark. That's actually pretty good, right? So I would suggest that we switch to these kind of formats wherever possible and only use JPEG as a fallback. By the way, this is some of our testing that compares the different formats against each other. AVIF in this particular case, as you can see, did outperform WebP, but it's a close fight between those two in a lot of cases. They do holistically outperform JPEG though. Okay, then use modern encoders. So even in the cases where you have to use JPEG, for example, as a kind of fallback, there are different encoders that provide better results, depending also on how much CPU you let it use. Okay, so this example is completely overkill. So Google has this encoder called Quetzli that uses the Border-Oakley metric and takes a few minutes to come up with the final JPEG. In this case, it's 20 kilobytes smaller than using just a reference library. Maybe don't use that because it takes a long time, but do play around with different encoders as well as services that effectively optimize cross formats, because some of them do end up doing a pretty decent job, even if you don't implement something that is dynamic based on quality metrics. I know some of these services that offer an API, for example, do that internally themselves, or just use CreativeLi. And then finally, compress before delivery. Here, it also relates back to that point around how you can actually impact what assets are served. So there are two types of ways to do this. One would be asset pre-compression. So using an encoder to come up with an encode ladder, and then using some kind of logic to decide which profile from that encode ladder to send through. That's how a lot of streaming websites work, for example. The reason why we also think this is good in terms of optimizing is because if you can use additional resources to build out that encode ladder, and this won't actually have a very big impact on your overall, overall what you're doing, as in terms of cost. Okay, you're doing that once, there's some additional CPU, but it's limited. And also in terms of time, there's no latency each time. And also in terms of carbon footprint, the carbon footprint of that additional time you spend encoding will be spread out and will actually be outweighed by the carbon footprint saved by the lower file size. If you do something very different, ad hoc compression, it's really hard to start dedicating more CPU to the encoder, because that would start introducing latency and also multiply the carbon footprint every time. So really there, I think it's more about using a better encoder, something that's more efficient, but there's a limit to how efficient you can make it before you start encountering issues because of latency. So in essence, if you have an encode ladder, it's much easier to play around with compression and come up with better results. If you're doing it ad hoc, which in some cases might be necessary, when you're doing things like DCO, for example, you can't really do it with an encode ladder sometimes. If you're doing it ad hoc, it's much harder to optimize for compression. And then finally, index PNGs. So we don't really look at the PNG format very closely when looking at how to optimize assets. That's because the PNG format is really about maintaining information. It's a lossless file format, although there are lossy implementations. But one thing you can do with PNG to really cut down the file size, and it's really simple, is to index colors. So with images with fewer colors, such as logos or text images, through color indexing, you can essentially achieve a fifth, a tenth of the file size potentially, depending on the resolution, colors, etc. You essentially limit the file to storing up to n colors, and can be 8, 128, 256, rather than the full range of the 16.7 million colors that are normally possible within a PNG file. So by doing that, you're able to minimize the file size quite drastically. In this particular case, for example, these two are virtually the same image. Only difference is with the one on the bottom, it's 5 kilobytes, whereas the one on the top is 20 kilobytes, by cutting down on unnecessary colors. And I think that is pretty much where we are right now with CreativeLi. In terms of next steps, as I mentioned, we're working actively on a couple of case studies, A/B tests between tags that send optimized and tags that send unoptimized assets. And we're also exploring other areas of lightweighting that have little to do with compression. For example, as I mentioned, lazy auctioning, lazy loading in general, and other ways to make ads effectively consume fewer resources while delivering the same or better outcomes. Any questions? All right. In that case, thank you everyone for joining. If you do have any questions, feel free to follow up over email. We will be making further updates on this work available as we progress. And I wish everyone a pleasant afternoon.
Thank you. Bye.
Bye.